Hi everyone, I'm Andrew Montgomery, a biology major on the pre-veterinary pathway and a member of the Franklin College class of 2022. And today I'm going to teach you guys a lesson on quantum numbers. This may sound like an intimidating topic, but I promise you'll be able to grasp the idea of quantum numbers and how to apply them to some chemistry problems you'll solve in your lecture by the end of this video. In previous chemistry courses or lectures, you probably learned about the Bohr model of the atom, as seen here. It is a series of rings drawn around the nucleus. Here I represented the protons and neutrons as blue and orange circles. And there are red electrons seen on these outer rings here. And for this example, our atom we're looking at is neon, which has a characteristic 10 electrons. So electrons fill the rings from the first ring outward. So the first one in a Bohr model only has 2 electrons. The second has 8, which is exactly how neon is, 2 and then 8. And then if it was a bigger atom with more electrons, the third would have 18, and so on. However, this idea of an atom is actually inaccurate and not a proper visualization of how electrons exist in orbitals around an atom. So we are not going to look at this at all. It turns out there's much more specificity to the levels and existence of where electrons are actually more likely to be found around an atom than the Bohr model implies. Quantum numbers, as you'll see throughout this video, is much like a filing cabinet. It's a series of numbers like a unique ID to find where a given electron may exist. These numbers build upon one another to become more and more specific and organized, much like the different levels of drawers and labeled files seen here in this filing cabinet. It gets more and more specific and easier to find the more organized it is. So let's begin. First, we'll start with describing the specific quantum numbers. Then we'll learn some rules, and then we'll apply them to some problems, which you'll probably see in your general chemistry course. First, let's walk through each of the various types of quantum numbers. The first number is the principal quantum number. It is represented by the letter N and signifies the shell or level. All orbitals with the same value for N are in the same level or shell, and the total number of orbitals in a level is found by the equation N squared. The lower levels are of lower energy, so it's like a staircase, 1, 2, and 3, moving to higher energy levels. The second quantum number is the angular momentum quantum number. It is represented by the letter L and divides the shell, that first N number, into subshells. This number is represented by a letter code, which is why I label this number the ABCs category, just as a memorization tool. The subshells for a level are found by the equation L equals N minus 1. As you can see here, each number of L is represented by a different letter. For the numbers 0 to 3, which is all we'll deal with for this video, those letters are S, P, D, and F. And it turns out they are of increasing amounts of energy. Each of these different subshells also has a different shape, which isn't important and will be discussed in general chemistry, but is outside the scope of this video. The last quantum number we'll discuss is the magnetic quantum number. It is represented by the letter M sub L, and it divides these subshells into individual orbitals, which is exactly like where a paper is inside the file inside the certain level drawer in our filing cabinet example. The number of orbitals per shell is found by the equation 2 times L plus 1. So for the P subshell, which has an L of 1, our M sub L would be 3. Therefore, there are 3 individual orbitals in a P subshell. The M sub L orbitals are labeled from negative L to 0 to positive L. That might sound confusing, but for example, if L is 1, which is the P subshell, we call the 3 P orbitals in order negative 1, 0, and 1. We'll further discuss that later. So now that you know a little bit more about each of the types of quantum numbers I wanted to discuss, we'll understand how this all comes together by following a series of rules that will aid this understanding. The first is the Pauli exclusion principle, and it states that no 2 electrons have the same set of quantum numbers. So each electron has a unique ID, or quantum number set. The Aufbau principle explains that electrons fill orbitals in a certain order from low to high energy. As explained, the lower N number is lower energy, and the various subshells are of increasing energy. The orbitals are of increased energy in the following order: 1s, 2s, 2p, 3s, 3p, 4s, 3d, And it goes further on as you move down the periodic table, but that's as far as we'll concern ourselves with. As you can see, at the very end, there is some overlap between N levels as we start to involve the D subshell. We'll not concern ourselves with the reasoning behind that, but that trend continues if we were to go on. The last rule is Hund's rule. This states that electrons fill equal orbital subshells one by one before pairing up. For example, let's look at the p subshell again. If we have 5 electrons in this level, they first go one by one, and then the opposite spin electrons fill these orbitals. Only these first 2 orbitals are filled because there are 5 electrons, so that last p orbital, the +1 orbital, does not have 2 opposite spinning electrons. Now let's apply our rules and knowledge of quantum numbers to some electron orbital diagrams. Let's start with a simple example like oxygen, which only has 8 electrons. To draw an electron orbital diagram, we first draw an arrow on the left side to indicate increasing energy. Then, following the off-ball principle, the general scheme for writing in the levels and subshells is seen as the following. We start with 1s, 2s, 2p, and go on, but this is only how far we need to go for this example. Now we can fill in our 8 electrons. It's pretty simple. Both s subshells are full. Then we follow Hund's rule in the p subshell. We first fill 1 electron into each of the p subshells, and then there's only 1 more electron, so we pair that with the electron in the m sub l -1. Now that we've filled out the diagram, let's go back and look at electrons in a certain orbital and how we can look at each of their quantum number set. So for the 1s level, let's go through that. It has an n of 1, and we know it's an s subshell, so L is 0. Using the equation 2 times L plus 1, we can figure out that ML is just 1. And then following the orbital labeling scheme, just because it only has 1 subshell, that orbital is just numbered 0. And it's the same for the 2s as well. Let's go back and revisit the p subshell. As seen in the diagram, the n is pretty obvious. It is 2. We know p is an L of 1. And then again, using the m sub L equation to find out how many orbitals are in the p subshell, we know that is 3. And then following the rule of labeling those orbitals, -L to +L, we know there's 3. And our L is 1. So that first orbital is -1. The middle one is 0. And the last one is just 1. We can also look at ions when using these diagrams, like the potassium ion, indicated by K+. Normal potassium has 19 electrons, as seen looking at a periodic table. So the cationic version would only have 18 electrons because it donated an electron to another atom, and it became positively charged. If we follow the same method of drawing to get us enough space to fill in the orbitals, we end up with something like this. I drew in the 4s and 3d levels here to highlight the overlap of energy levels as discussed with the Aufbau principle. If you fill in all 18 electrons, you'll see that it has a full valence and is equal to an argon atom, which is a noble gas with a full valence. So it turns out when you look at the electron orbital diagrams, this potassium ion is actually the same representation as argon. Electron configurations is simply condensing what you see in an electron orbital diagram by writing the element symbol. In this case, we're looking at ion, so K+, and then writing out all those energy levels and how many electrons are each, indicated by a superscript. So for this case, 1s2, 2s2, 2p6, 3s2, and 3p6. And if we total all those superscripts, in this case, it equals 18 electrons, so you know you did it right. I hope these examples helped you to visualize the usage of quantum numbers, and you should be able to apply this information to solve your own examples of filling in electron orbital diagrams, as well as writing electron configurations.